Okay guys, welcome back. Hopefully by now you've figured out how water flows. Hopefully you've figured out that when you pour something, the back of it has to be a little bit higher than the front of it. And that gives the water at the back a little bit more gravitational potential energy than the front. And that makes the water molecules kind of roll over each other and go from one place to another. So that's kind of the driving force on water. But of course we're going to have a similar idea when it comes to electricity, and that's going to be potential difference. Of course we should probably ask then, how do I make it flow faster, or how do I make it go slower? So you could probably guess here, I don't have a whole pile of current because the back of it is not quite as high. But in this case, if I tilt it more, then I get a much faster flow. So it should make sense that the higher the tilt of the glass, then the faster the flow of current, or the higher the current that we're going to get in our electricity equations. In a similar way, there's another way that we could actually make water flow. And I wouldn't necessarily have to tilt it. If I tilt it right up, not much happens here in this case. The bottle of oatmeal is full of water, but there's almost nothing falling out of it. Can you think how I might make water flow now? What do you think? If I squeeze the side of the bottle, then that will drive water out of it. And of course that's another way that we can think about this. It's a driving force that's going to make water flow. And what I'm trying to explain to you now is that that driving force is a lot like the potential difference or the voltage that we're going to get in our voltage equations. Oh, one more thing before we leave it. So we've got current, which is the flow of water. We've got the potential difference or the voltage, and that's kind of like the tilt on the glass. There's one last concept that we've kind of skipped over here, and that's the resistance. And that is basically how much the top of the cap resists the flow of water. So you can see here the resistance is quite high. But of course if I squeeze it, then I can still get a decent current to flow. Whereas here the resistance is quite low, and the water will flow quite freely there. So that's our, we've now got current, charge and time, which we dealt with the last day. Now potential difference or voltage, and that's going to be measured in volts. And now we've also got the idea of electrical resistance. Okay? So before we get into doing calculations on this, I'd like you guys to come back to your analogy. This is my water analogy. Again, I want you guys to come back to your own group analogy and ask yourself two questions. Number one, ask yourself, what is the driving force? What is it that makes that thing that you came up with the last day actually move? Okay? And then ask number two, what is it that slows them down? What's the electrical resistance? What's the blockage in the line, or the size of the cap, or maybe the size of the hole that the water is trying to get out through? What is that in your analogy? Take about 5 minutes, discuss that, and see if you guys can add that into your poster that you made from the last day. Best of luck with that.